Hello everyone, today we're going to be working on an example for a structures problem, and this problem or example is asking us to find the reaction components to determine the member end forces and the moments, and to draw the shear and bending moment diagrams for beam BC. So as you can see with the figure that is given to us, we have a pin support at point A right here. Then we have a roller at point D, and then we have a moment going on at point B. So to start off part A, we need to recall that a roller will only have a restriction on the y-axis, which is why we have a y force right here. We'll call that d of y. From there, since A is a pin, we have a y force. We'll call that a sub y, and an x force. And we shall call that a of x. And in the beginning, we're just going to assume the direction that it's going. So for vertical forces, you could assume upward, downwards. For horizontal forces, you could assume right or left. It doesn't matter, because in the end, once you solve for them, you'll be able to tell in which direction they're actually going. So to find the reaction components, we have to keep in mind that our forces in the x direction have to equal 0, our forces in the y direction have to equal 0, and our moments have to also equal 0. So we're going to start off with our x forces since we only have one. So it is assumed that right is positive, and we know that the sum of our forces in our x direction have to equal 0. So that means that we have to write out all of our x forces and equal that to 0. As you can see in this example, we only have a of x. And so that means a of x will equal 0. So after we solve for the forces in the x direction, we can tell that in a way we could negate that force. That force is non-existent in this example. Next, we're going to continue on with our y forces. So we assume that going upwards is positive, and we know that the sum of our forces in the y direction also have to equal 0. Here we have d of y, and we assumed that it's going to go upwards, so that's positive d of y. And then for our a sub y, we assume that it's going downwards, so that's a negative, so minus a of y equals 0. If we were to solve that out, we know that d of y is equal to a of y. And that's the most that we could do as of right now for our forces in the y direction. So to help us solve for our forces in the y direction, what we're going to do now is proceed to our moment reactions. And we are going to work or solve for any moment reactions about point A. And you'll see why in a bit. So once again, we know, let's make this a bit smaller. Mm, it does not want to get smaller. Okay, that's fine. Anyways, as I was saying, our moments also have to equal 0, and we are going to take our moments around point A. And we're going to take it about point A because of the fact that, if you guys remember, that if a force intersects an axis, the force will not produce any moment about that axis. Or if the force is parallel to an axis, that force will not produce any moment about that axis. So In a way, what we're trying to do is we're trying to pick a point where one of the y-axis will not have will not produce any moment about that axis. Because if we solve for one, then we could solve for the other one because we were able to figure out that d of y is equal to a of y. So we could, in this situation, we could either take it about point A, and if we take the moment about point A, we could solve for d of y, but we could also take it for take the moment about point D, and then if we were to do that based on D, we would be able to find the force AY. But I'm just going to do it about point A. So we know that it is assumed that counterclockwise is positive, and we know that the sum of our moment reactions about point A have to equal 0 as well. So like we mentioned earlier, ACE of Y is parallel to that point. So it will not cause any moment. So that's assumed to be 0. From there, we have a moment going on here at point B of 50 kip feet. So, and that is going clockwise. So that's going to be a negative 50 kip feet. And then from there, we have our d of y. Since remember that the force that the moment is equal to the force times the distance. So to start off, this force is assumed to be going upwards, right? And about point A, since that thing is going upwards, that's going to cause a counterclockwise force, counterclockwise moment, which is why that's going to be positive. The moment of that's going to be positive. So we have a positive, we have our force, which is d of y, that we're trying to solve for. And then the distance is 10 feet because this is a vertical force. So we have to shift it that way so it could align with point A. So times 10 feet. And we know that has to equal 0. So if we were to move over the negative 50 kip feet to the other side, we have 10 d of y is equal to 50, positive 50 kip feet. From there, if we were to solve for d of y, we know that d of y is equal to 5 kips. And since 5 kips, and remember, we assumed that d of y was going upwards, so this is 5 kips going upwards. And since that turned out to be a positive number, that means we assumed correctly. So for example, if we would have assumed that our d of y was downwards, assuming it was going downwards, we would know that since about this point A, since that force is going downwards, it was going to create a clockwise moment. Because think about it as like a steering wheel, that when you pull down on that steering wheel, you end up creating that steering wheel is going clockwise. So since it's going clockwise, that would be negative. So that would have changed the sign right here. It would have been a negative. So that would have changed your answer to being d sub y equals negative 5 kips going downwards. So it would have looked something like this instead. But we don't like working with negative numbers. That negative is showing that you assumed incorrectly. So to fix that, you would rewrite that as d sub y is equal to 5 kips going upwards. So it doesn't really matter if you assume downwards at the beginning. In the end, it will tell you if you assumed correctly or assumed incorrectly. We assumed correctly in this situation, so we found out that d sub y is equal to 5 kips. We know that our a of x is equal to 0, kips, and we still have to find our a sub y. But if you guys remember, our a sub y is equal to our d sub y. So that means that our a sub y is also equal to 5 kips. And remember, we assumed here that a sub y was going downwards, right? And we know that all of our vertical forces downwards is negative, positive is upwards. So in this case, if you would have assumed that a sub y was positive, like going upwards, you would have had something like this. D sub y plus a sub y is equal to 0. So you would have gotten that d sub y is equal to negative a sub y, right? And so in a way you would have assumed that a sub y, so negative a sub y, sorry, that your a sub y would have been the negative version of your answer of d sub y. So you would have gotten that a sub y is equal to negative 5 kips going downwards. Sorry, going upwards, because this is an example if you would have assumed going upwards. But again, we want positive forces. So you would have ended up getting that your 5 kips is being applied downwards. So like I mentioned earlier, it does not matter in which direction you assume, because in the end, you will end up getting the same answer. That's just something to keep in mind. I'm sorry for talking about that a bit longer, but I just wanted to make sure everybody understood why assuming doesn't really matter, because in the end, everybody will get the same answer. So just like that, we were able to solve part A of where it asked us to find the reactions. I don't know why it's not working. Okay. So now it's asking us for part B to determine the member end forces and the moments. So that looks like is basically what we're going to do to this figure right here is we're going to split it up member by member and determine those member end forces and those moments that come with it. So what we're going to do for part B, this is for part B, is we're going to redraw that figure that we're working with, that structure, but this time we're going to leave some space between each members. So we have beam, or that segment AB, where we had that pin, and how we solved it earlier, we know that there is a vertical force of 5 kips acting downwards. This is point A. This is point B. From there, we know that it has a length of 10 feet. From there, we have point B. And on point B, there is that moment occurring of 50 kip feet. I'm sorry, you guys. 50 kip feet. But instead of showing it as a point, I'm gonna show it as that corner right there. So now that we know that, now we could proceed to beam BC. This is beam BC right here. We know that that is also 10 feet. And then from there, we have a beam CD. We have a roller. And we know that we have 5 kips acting upwards on that point. So now that oh, sorry you guys, I forgot to draw out the corner of C. This is corner C. There you go. Okay. So now that we have that, to solve for our member end forces, you could either work, you always want to start off on like at an endpoint. So we could go about this two ways. We could either start off with beam CD or beam AB, and then from there work our way through the structure, or this way. In the end, you'll get the same answers. So I'm going to start off with, let's start off with AB, just to go in alphabetical order. So since, as you can see here, we have five kips going downwards. And when you're solving for member end forces, the point is you want everything to be balanced out. So if we have five kips going downwards, that means here we have five kips going upwards. Let's make that a bit more visible. So that means we have five kips going upwards right here. Sorry, you guys. We have five kips going upwards. And as you can see, with adding those five kips, that's perfectly balanced out. We don't have to do anything. So now we're going to proceed. Now we go on to that corner of B. As you can see, since we have five kips going up right here, that means we have another five kips going downwards to cancel out those five kips. And since we have, so we drew this five kips because we have our five kips right here. So that means we need the opposite, the other side to have that opposite force going down. So that's our five kips. Now looking at just the corner of B, we now have to balance this out. So here we have five kips going downwards. So that means we need five kips going upwards to balance that out. And as you can see, we have a moment going on counterclockwise right here, a 50 kip feet going clockwise. So that means we're going to need 50 kip feet of a moment going, but now counterclockwise. And now with that, all of our forces are balanced out. So now we proceed to beam BC. As you can see, we drew a counterclockwise moment on the corner of B. So that means we have a clockwise, um, sorry, no, this was clockwise, sorry, this was counterclockwise. So that's why we drew a counterclockwise moment, sorry. And since we drew a counterclockwise moment right here, we are going to be drawing a clockwise moment acting at the end of beam BC on the B side. So we have a clockwise moment of 50 kip feet. And remember that the last force that we drew was this five kips going upwards to balance that out. So if we have five kips going right here, that means we have five kips acting downwards on this side. Okay, so now looking at this beam by itself, since now we added everything that we added to here onto here, that affected, well, this side of the beam. Now we look at the simple beam BC. We have to balance this out. Since we have five kips going downwards on the side of B, we need five kips going upwards on the side of C to balance that out. Five kips. And as you can see here, now we have what is known as a couple force. We have this force that's going upwards, this force that's going downwards, and if you guys know, this is going to create like a moment. This creates a moment. So in a way, since this side's going upwards, this side's going downwards, it's going to be creating like that. Let's see if I could show it. It's going to be creating, do you guys see this? A counterclockwise moment, right? And because of that, with by the couples, we are creating that counterclockwise moment. And we have a clockwise moment going here. So we don't have to add a counterclockwise moment right here, an extra one, because that fifth because that these two couples are already creating that 50 kip feet moment, that counterclockwise moment. And we know that it's 50 kip feet because we have 5 kips and it's a span of 10 feet. So that gives you 50 kip feet moment. So now that that has been balanced out, we're going to proceed on to the to the corner of C. We have our 5 kips right here. So that means we have 5 kips going downwards. And since we have 5 kips going downwards on this side, now we have to balance it out. We have to apply 5 kips going upwards. Now that that's balanced out, that doesn't create a moment because those are just two vertical forces. So since we have 5 kips going upwards on the corner of C, we have 5 kips going downwards on this part. And now just taking a look at beam CD, we are now going to balance it out. As you can see, we have 5 kips going downwards here, and we have our dy force of 5 kips already acting upwards. And as you can see, we don't have to add anything else because it's already balanced out. And that's basically how you check if you not assumed, if you solved for your member and forces and moments correctly. Because if you were to start off on this side, when you end on this side, it should already be balanced out. If for some reason you ended up with that 5 kip feet going downwards, but you also ended up getting like this moment of going this way, that means you did something wrong. You took a wrong step previously before, and you should go back and check where you added an extra moment, an extra force, anywhere. But if you did it correctly, that means that in the end, it should already be balanced out, and you don't need to do anything else. So that's the answer for part B, where it asks us to determine our member end forces and moments. I'm sorry if it's a little bit messy. I'll try to be neater on another example that I'll do. And now it's asking us to find, sorry, not to find, to draw the shear and bending moment diagrams for beam BC, as you can see. So now we're going to do part C. So part C, it's asking us to find, sorry, I don't know why I drew arrow, to draw the shear and bending moment diagrams for beam BC. So if we were to draw out our beam BC, we know that that's 10 feet. And if we were, as you could tell, we know that there's a force of 5 kips acting downwards, and we have a clockwise moment of 50 kip feet acting right here. And we know this because remember, we already determined the member and forces of each of each uh, of each beam. So we took that information from right here. So now that we know that, now we add the information also for this side of the beam, which was just the 5 kips going upwards. Now, if we know, we're trying to find the shear and bending moment diagram for beam BC. So to find that out, we just have to cut in a way somewhere on our beam right there, and we decide which side to work with. Before we decide which side we want to work with, I just want to remind you guys about the sign convention. that if you were to cut a beam, and if you were to have the cut on the right side of the beam, you would know that your shear force would be going downwards and that your moment will be acting counterclockwise. Meanwhile, if your cut is on the left side of the beam, you know that your shear force will be acting upwards and that your moment force will be acting clockwise. So just to take that into account, I'm gonna work here with my left side of the beam. So now that we know that, we're gonna draw out our left side of the beam. We have our cut right here. And like I showed you guys earlier on, based on our sign convention, we know that we have a shear that's going down and that we have our moment going counterclockwise. From there, we know that we already have a force of 5 kips going downwards on this side and that we have a counterclockwise moment of 50 kip feet. We don't know the distance of this beam. We don't know the length, so that's why we have that length as x feet. And that's why we, right here, we annotated our shear and moment diagram with x, because we don't know exactly how long that is where we cut right down the beam. So now we're gonna just solve for our shear and moment diagrams. So as you guys remember, the sum of the forces in our y direction have to equal 0. We didn't do this for the x because we don't have no x-axis, sorry, no x-forces, because here we're only dealing with shear and moment. So shear is vertical, moment, well, is that moment acting. So we know that has to equal 0. So we have that negative shear moment going on right here. So that's negative v of x. And then on the other side, we also have that negative 5 kips. So minus 5 kips is equal to 0. So if we were to solve for our shear, we would get that our shear is equal to negative 5 kips. Now we're going to go on and proceed to find our moment. We know that our moments have to also equal 0. And here we have a clockwise clockwise moment of 50 kip feet, and then we have a counterclockwise moment at point X. So this one's negative, this one is assumed to be positive based on our sign convention. Because remember, we assumed that counterclockwise is positive and upwards is negative. So we have the negative 50 kip feet plus 50 kip feet plus that moment at x that's occurring. But remember, we, we're taking, sorry, I didn't clarify this. We're taking this moment about this point right here. We're going to call that point O, which is why I wrote here that the sum of the moment about point O has to equal 0. So we have our 50 kip feet. We have our positive moment happening right there. But remember, we have this vertical force that's on this side of the beam, which is going to cause a moment about that point O. So we have, remember that moment is force times the distance. So that moment is going to be equal to this 5 kips times the distance of x. And this is going downwards, as you could see, right? And about this point right here, if we have a force going downwards on this side, that's going to create a clock, not a clockwise, a counterclockwise moment, which is why that's going to be positive. So plus the 5 kips times the x feet that we don't know is equal to 0. From there we solve. We know that m, the moment at the moment of x, oh, the moment of x plus the 5x kip feet is equal to 50 kip feet. From there, we know that our moment is equal to negative 5x kip feet plus the 50 kip feet. So now that we found our shear and moment, we can now draw that diagram. So we're going to use these things that we found to draw out our shear and diagram. So we're going to start off with our shear. As you can see, shear is equal to negative 5 kips. So if we were to draw that diagram, we have our y-axis right here. We have this x-axis right here. We know that our beam is 10 feet long, and we found that our shear is negative 5 kips. So that means that our shear diagram, we're going to put this as this is negative 5, this is negative 10, this is negative 15, this is positive 5, positive 10. We know that that shear is 5 kips, negative 5 kips. So that is our shear diagram. It's straight. It's constant. There's no variables in that shear, so it will always equal negative 5 kips. Throughout that whole beam, there's a constant shear force of negative 5 kips. Now, if we were to draw our moment diagram, we have our y-axis right here, x-axis right here. We know that our beam is 10 feet long, and this is our moment on that y-axis. Our x-axis is the length. I should have probably also specified that here, that our y-axis is our shear force, and then our x-axis is the length. So here, so looking back at that, of this equation that we got that the moment is equal to negative 5x kip feet plus the 50 kip feet. So as you can see, we have a constant. We don't have a constant, sorry. We have these 50 kip feet that don't change. So that means that we start off this. I'm going to do this 25. No, actually, let's move this down a bit just so we have more room to work with. Okay, every dash is 10 feet. So 10 feet, sorry, 10 kip feet. So we have 10, 20, 30, 40, 50. So this is where we start off our moment diagram, that 50 kip feet. And then from there, we know that for every, we have this negative 5x kip feet. So what we could do is we know that our beam is equal to 10. So, and as you can see, our distance is represented by x. So if we were to plug in negative 5 and then 10 feet for our x, we would end up getting sorry, If we were to use that equation right there, m of x will equal to -5 times, we want the ending, so times 10 feet plus 50 kip feet. So from there, we were to solve, we would get -50 kip feet plus 50 kip feet. That means that our moment force at the distance or at the length of 10 feet is equal to 0 kip feet. So that means that our moment right here at the 10 feet would be at 0. Our moment at that 0 feet is equal to 50 kip feet because if we were to plug in 0 instead of 10, if we were to plug in 0 feet for right there, you would see here that, well, -5 times 0 is 0, so that would just leave you with that the moment at 0 feet is 50 kip feet. Now, what you could do is you could just draw a line connecting that, showing your moment. But if you want to be a little bit more precise, what you could do is like for every 2 feet or every feet, you could just plug in that distance and end up getting the moment, and then you could plot more points. I'm just gonna assume that line, but like that, we were able to also determine, well, to draw out our shear and bending moments for that diagram. Sorry, we were able to draw our shear and moment diagrams for the beam BC.